Okay, so on Friday, we learned about how to write electron configurations, and we learned about how to write orbital notations. And so at this point, you probably don't need a cell phone for this, because if you're unclear as to about how to do it, it would be really, really important to pay attention. Or if you didn't do the homework, it'd be really important to pay attention so that you can learn the new skill on how to do it, in which case requires a lot of paying attention and not a lot of cell phone usage. So here we go. Here I've got a good old-fashioned blank periodic table for you to take a look-see at. And what I'm going to do is I'm going to give every one of you a brand new copy of the periodic table. Brand spanking new, fresh off the presses. It's so new.
Is it still on?
No. It's so new it's cold. I got nothing. I'm just trying.
It's okay.
Now, I know that you have periodic tables. I know you have one in your possession. You may recall that my periodic table's name was Jethro. This one might be Sarsaparilla. I don't know. But we are going to name our periodic tables, and because they're going to be our best chemistry friends. The reason why I'm giving you this periodic table is I'm going to ask that you write a bunch of stuff on this periodic table that you will not use much after this unit. So putting it on your good periodic table, your chemistry periodic table best friend, might be like too many tattoos. It might be like all those face tattoos that nobody wants. You know what I'm talking about? You want a face tattoo? No?
Yeah.
I don't know what that means. So the next thing, so what I want you to think about is, so the periodic table was actually sort of kind of set up by a gentleman named Dmitry Mendeleev before we knew much about what the atom actually looked like on the inside. And so he basically decided that instead of writing all of the elements that we know in alphabetical order, which is what we've been doing up until that point, that he was going to organize the elements according to physical and chemical properties that we knew of. So basically, he just made a bunch of piles of elements that had similar physical and chemical properties, like dissolved in water, for example. And as a result of that, he saw common trends, where he saw common properties just kind of keep showing up over and over and over again. And when he arranged his periodic table, the periodic table that we have today isn't that far off from the periodic table that he made like in the late 1800s. We know a lot more elements. We've made some adjustments, but for the most part, the periodic table is pretty much the same today as it was in the late 1800s. Now, the reason why I take some time to talk about that is because there are things that we know about the periodic table that fall into place, even though Dmitry Mendeleev didn't know anything about how the atom was set up and where electrons existed around the nucleus of the atom, which is what electron configurations are. So, if we pick any element, it doesn't matter which element, but let's just say we pick the element that happens to be, I don't know, right here. If we locate that element in the periodic table, you would tell me that element is chlorine, correct? So I'm going to erase that dot and put chlorine, right? I know that by simply looking at its location on the periodic table, I know it's going to end its electron configuration with 3p5. And it has nothing to do with things I've memorized, and more to do with I know how the periodic table is set up. So if I grab an element like zinc, I know that it's going to end its electron configuration with something like 3d10. And if I use an element like strontium, I know that it's going to end its electron configuration with 5s2. Now, the reason why I'm taking the time to show you that is because the periodic table actually happened to be organized according to some other pieces of information that you may or may not remember. So, for example, you may remember that anything that the S shape can hold how many electrons?
1.
Try again.
2.
2. It can hold 2 electrons. And you might recall that the P shape can hold how many electrons? 6. Well done. And you might recall that the D shape can hold how many electrons? 10, right? And just for, I guess, funsies, right? You might remember that the F shape can hold how many electrons?
4.
1, 4. Good. Now, here's the beautiful thing about the periodic table. Everything that is in this column right here will end its electron configuration with something S2. And everything that's in this column right here will end its electron configuration with something S1. How I know what that's going to be is based on this knowledge here. Does anybody happen to remember how many energy levels I said that could potentially exist in the nucleus of an atom? Around the nucleus of an atom, the answer is 7. This periodic table happens to have 7 rows. Okay? All of the elements that are in these 2 columns and this one are in what we refer to as the S block. And you might want to like mark up that periodic table that I just gave you. It's the S block. So everything in column 1 is going to be something S1, and everything in column 2 is going to be something S2. Now, if I were to like draw a box over here, how many columns are in this purple box? 6. Which shape holds 6 electrons? P. So the purple box is called the P block. And it depends on which row it's in, but it'd be something like P1, P2, P3, P4, P5, P6. So here I have a different box, this yellowish, goldish color. How many columns are in this box? 10, right? Which shape holds 10? D. So this is going to be the D block. And the shape that we're not going to spend a lot of time with is here, and that's known as the F block. Like I said, we're not going to spend a lot of time there. Going back to the D block, this would be something like D1, D2, D3, D5, D6, D7, D8, D9, D10. Now there's a wrinkle, and this is going to be kind of important that you might want to write in the space between the S and the D block. You might want to write a 3 here, a 4 here, not a 6, a 5 here, and maybe a 6 here. Because if you might recall from Friday, it went like 4S2, 3D10, and then back to 4P6. You might recall that from Friday. So I'm trying to have you remember that. So there's the beauty of the periodic table. The periodic table was essentially set up before we knew about the location of most of the electrons. And the periodic table, for most part, matched where the electrons are. That's beautiful. Now,
where's the S block?
The S block is the first 2 columns.
Oh.
Yep. Oh, yeah. So let's take a second and see how we can use the periodic table to help us identify the electron configuration for an atom. So the first element that we're going to do is something simple like boron, which happens to have 5 total electrons. Now what I'm going to do is I'm going to go back to my periodic table. And I'm going to start in that first row, that first energy level, because we always start closest to the nucleus. And I'm going to go 1s2, 2s2, and we're doing boron, so we're going to stop right here because that's where boron is. So I went across the first row, 1s2, went through the second row, 2s block, so 2s2, and I'm going to end in the p block of the second row, 2p, in this case 1. So I use that to get to the electron configuration, which is 1s2, 2s2, and 2p1. And if I were to draw the arrow notation, it would be 1s, 2s, 2p, 2p, 2p. And then I'm going to have my orientation bars. And then I'm going to start filling in electrons. Arrow up, arrow down, arrow up, arrow down, arrow up. And then if I wanted to go ahead and identify the number of valence electrons, I would look for the biggest energy level. So in that case, it's 2. This is the biggest energy level. So I'm going to add the electrons together, and I get 3 valence electrons here. The next one we'll do is aluminum, which has got 13 electrons. So I'm going to go back up to my marked up periodic table, and I'm going to start in the first row, and I'm going to go 1s2, 2s2. Oh yeah, we're doing aluminum, so I'll fill that in, right? So this is aluminum right here. Okay, so yeah, back to 1s2, 2s2, 2p6, 3s2, 3p1. So when I take that information, I say that it's 1 S2, 2s2, 2p6, 3s2, 3p1. And so if I was to draw the arrow notation for that, okay. If I go ahead and I look for the biggest energy level, in this case it's the 3 is the biggest energy level. 2 plus 1 electrons is 3 electrons. Now, what I like to point out is that boron and aluminum are in the same column of the periodic table. Boron and aluminum have similar, in this case, physical properties, that is where the electrons are located. So that's kind of something to consider. Does this make a little bit of sense? Does anybody have any question that they could ask?
Can you show how you're reading through it, like on the periodic table?
Instead of my blank one?
No, yeah, on the blank one.
Instead of doing it on the blank one, on a different blank periodic table, because I have one of those called up, ready to go.
No, do the old one, and then go like slowly.
Okay, so we have, the next one is vanadium, which has 23 electrons. Okay, so if I go and I locate vanadium on the blank periodic table, vanadium is located right here. Okay. So if I start where I would always start, which in this case is going to be at the top, I would go 1s2, 2s2, 2p6, because it's really 1, 2, 3, 4, 5, 6, 3s12, 3p, 1, 2, 3, 4, 5, 6, 4s2, 1, 2, and then I'm going to go down to the 3d, so it's going to be 3d, 1, 2, 3. So where it is in the periodic table is in the third energy level, the D block, and the third row in, third column in, making it 3d3.
Oh.
So if I translate that into numbers and letters, right?
Oh, I get it.
It becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So if I translate that into the arrows, I get something like this. And then I added my arrows. And I end like that. If I want to identify the number of valence electrons, biggest energy level is 4. So that means that there's going to be 2 valence electrons. I want you to try chlorine, which has 17 electrons. Go ahead and try that one now. Okay, so here we're going to give this one a quick try. We are doing chlorine, which is the element over here, which we'd already identified should be 3p5. So I'm going to go 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 3s2, 1, 2, 3p, 1, 2, 3, 4, 5. So when I go down and I look at my answer, I had 1s2, 2s2, 2p6, 3s2, 3p5. And I noticed that the biggest energy level is the third energy level. 2 plus 5 is 7. Questions?
Yep, right.
Okay. Your homework is to do worksheet number 6. It is a one-sider. You have a bunch of time to try it. Good luck.